All right, welcome back. I wanted to share a little bit of a new discovery for me. It's a new RStudio package called tfruns. And what this does is operationalizes grid searches for TensorFlow models fit through the RStudio package. And so what I thought I would do is walk through an example. It's a new package. There's not a lot out there on the web. So what I'm going to do is load the packages. And I have a relatively large data set right now, and it's going to take some time to load. And while it's loading, I'm going to switch over and show a little bit about what the training task is. So we're interested in predicting what is known as the background parenchymal uptake. It's affectionately known as BPU. And it's a measure of the tracer uptake in a woman's tissue. And it ranges from photopenic, where it's dark, and all the way up to where you start seeing moderate to marked in uptake. And the tracer shows as bright white on this. All these women have what are known as dense breast tissue, and so you can see how each of these images looks similar while the anatomy is different. You see that each of those, if there was a lesion within this white mass, it would be hard to detect. So our goal is to be able to automate a predictive algorithm to classify MBI exams into photopenic, minimal, mild, moderate, and marked uptake. This is a new lexicon for grading what are known as molecular breast images. And it would be nice to be able to have some automated way of doing this, as well as some reproducible means for future research. So at this point, my matrices have loaded. I have a test matrix that is, I could probably tell you the size right quick. So it's 24,639 images. Each are 128 pixels wide and tall, and there's only one color channel. Our test data, which we've held out and we're not going to train against, is 6,172 patient exams. And what's exciting about this tfruns program is you can pass through a series of tuning parameters that you want. So I'm going to switch over right now, look at this program keras BPU. And I call it skeleton because it's a basic framework. And so what's new in this package is you can define an object called flags, and each of the flags has some named entities. And right now I have it set up to just look at a couple of things I want to be able to tune. Within this program, the default values can be set, ranging how many images at a time do I want to try to train against, how many epochs do I want the model to go through, do I want to do real-time image augmentation to the model, and then for right now I have only two parameters in terms of the network architecture. How many hidden nodes do we want at the end of the convolution cycles? So defaults are at 100, and for now I've turned that image augmentation flag off. We can go through, we have 5 categories of BPI. We can come back, and eventually I'm going to have this program generalized where I'm going to set some of these other parameters as tunable parameters within the tfruns framework. But for now, some things are set. To make the model run a little faster for this video, I've marked out several of the layers just to make it a little less computationally intensive. You can see in this dense layer where I'm passing the hidden 1, and then hidden 2, and then hidden 2. You go through, you optimize it. I'm going to put some parameters on the learning rates and in the future. You can see the passing here to see whether or not we're going to do image augmentation. Image augmentation allows for flips and various other sort of modifications of the original data structure of each image to make the model a little less fragile. And then an exciting thing, which I'm going to show you in a moment, is that you can save the models. And tfruns packages all this, so you don't necessarily have to create a script to make a unique file name. It will automatically trap all the output and put them into a nicely contained directory. So at this point, I'm going to run this. This won't take too long. I have a Titan XP GPU running on the iMac, or the MacBook Pro in this case. You can see it goes through, it creates the architecture it automatically, and so it did all the variable substitution. We'll see how it works in the viewer tab. It's loading up. I put the computationally expensive part of loading all the data outside the for loop, so it loads the data once, and then it's locally referenced within the skeleton model. So that's a nice feature. When I was first doing it, each time I would submit it, it would try to load the data, which ceased to be fun after a certain period of time. So the start, I'm only using 2 epochs for each of these combinations. It's not enough to get any meaningful performance out of this model, but it does show you how fitting TensorFlow in RStudio is just very nice. It's much better than working through a native Python installation. You get real-time tracking of what the loss functions are looking like. It does some graphing, and normally you would obviously go through and save more. And so you can see it wrote out the data. Now it went through, it's changed the architecture. It's using the next parts of the for loop. And this model is now programmed and ready. So we'll give it a few seconds. It moves relatively quickly at this point. As I've started exploring and trying different things with deep learning, one of my challenges is how do I know enough Python to be successful, and how do I relearn all that I know within R and Python? And it's turned out that with these newer implementations of TensorFlow through R, I'm finding that I don't really need to know as much Python as I feared I would need to. This type of modeling is quite readily implemented. It's still using Python on the back end. It's just R is doing all the translations and saving me the time of having to Google all the translations myself. So I think this is the third option in the for loop. The final one will come out shortly. You'll see I have a couple other commands written. It's give you some idea what those are going to do in a moment. But as you can imagine, latest run is going to give us an actual detailed report of what the last run was. And in this case, I'm using 20% validation split of my training data to look at the internal validation, and haven't actually trained against the test data at this point. So we're going to start the last of the 4 that I've run for today. Give it a few more seconds. Right. So that's now done. So you can see it's completed. If you want to get just a basic text summary of what it fit, you can just type in latest run. There's some other commands as well, but you can see each run goes into its own directory. It's indexed by some timestamp. You can see what the tunable parameters were as we passed through. You can see some information about the architecture. It's good. I wouldn't say it's great. You do get, if you want to look at the actual processing times, you can go dig it out. Something I do like is this comparison. And what you're able to start seeing is between 2 runs, and so it defaulted and picked the first 2, but you could have specified any in any pair that you wanted. Shows you where the loss is, the accuracy, gives you an idea what the difference is in the parameters and the flags. It shows you how it changed the network architecture and how it influenced the number of parameters. And that's quite useful, particularly if you see things maybe either degraded significantly or took a lot longer to run than you would expect. There are some high-level programs written that allow you to peek into what those directory structures are. Here's some. I have a couple of runs that I aborted along the way. But you can look here, you see the performance, and that's reasonable. You can take each of these names or use just this latest run for now. You can look at that as an object, and you can see that it defines automatically several parameters that could be of interest. You can go back and look at performance and do your own analysis to look at how performance maybe changes over some of the grid of parameters. But you can also easily access and build your own model. So I'm going to pull out the run directory. We're going to paste it in with the file that was saved. This is the whole network architecture, including all the saved weights. I can create a model path relatively dynamically, put it into a model, and now I can use this model, one of many models that I've already trained, and do some prediction on the holdout test data. And for now, this max call undoes the two categorical. It's something I'm surprised there's not a maybe a more direct reference to that, but it's something I found. And you can look at the cross tabulation. It's a simple confusion matrix here to look at how well the BPU is predicting. So right now, the prediction accuracy probably looks good. There's a majority of the cases being predicted with this BPU category of 1, which is may need to be re-indexed slightly, but that's something I can do. So overall, I'm excited. This is going to make the idea of tuning TensorFlow models in R much easier, give you a way to document and be able to recreate some of the analyses you may have completed already. All right, that's all I have for now. Thanks. Bye-bye.